non-inverting amplifier. So in this case, you can see we have applied input at the non-inverting terminal, and this inverting terminal is grounded through a resistance. Now from the previous concept, we know that if we apply this kind of feedback, if we connect output to input through resistance or any other element, it will give some negative feedback, and as a result the difference of the signal will be reduced to zero. So when the difference is zero, so if this potential is Vi, so same potential will appear here. So voltage at this node will be Vi. So this node Vi, same voltage will appear here Vi, to make the difference zero. Now if I apply KCL at this node, we can write Vi minus 0, Vi minus 0 by R plus Vi minus V0 by Rf equals to 0, or taking common Vi, V0 will be 1 plus Rf by R Vi, or voltage gain V0 by Vi, voltage gain is 1 plus Rf by R. So as you can see from the expression that it is a positive sign, so the gain is positive here, so it will not invert the output. So input and output will be in same phase. That's why it is known as inverting amplifier. Now we can do a variation of the circuit. Second circuit will be same circuit, and the input is connected through a voltage divider. So input is connected through a voltage divider R1 and R2, that is Vi. So input is connected through a voltage divider, and rest of the circuits are same. This we do because to avoid any damage of the op-amp, we do not apply the input directly, rather we apply input through a voltage divider. So first we need to determine voltage at this node. So it is simple voltage divider, and there will be no input current into the op-amp. So voltage at this point may be Va. So Va will be Vi by R1 plus R2 into R2. So this Va means that voltage also be Va, and you already know if that voltage is Va, in this case it was Vi, so output was Vi into this one. So if this node voltage is Va, so V0 will be 1 plus Rf by R into Va equals 1 plus Rf by R into R2 by R1 plus R2. Next we shall combine the inverting amplifier and non-inverting amplifier together in a circuit. That circuit is known as differential amplifier or subtractor. Differential It should be noted that op-amp itself a differential amplifier, but however you cannot control the gain of the op-amp. So we do indirectly, so we will realize a circuit using op-amp which gain we can control through external resistance values. So let's draw the circuit. So that input will be V2, R1, R2, V0. So this is similar to the inverting amplifier, and here we'll apply another input through a voltage divider. So here you can see that you have two inputs. One input at the inverting terminal, a non-inverting terminal, another input is at the inverting terminal, and output will be taken from here. We need to find out the expression of the output. We can do this in two ways. First way, you can do this in through superposition law. You can see we have two sources, so we'll take the response of each source individually and then sum it up. So first we shall use the method 1, superposition. So first we will consider the source V1. At this time V2 will be 0. So resultant circuit will be and output will be V01. So due to the source V1, output is V01. We have already computed this V01. So V01 will be, as already computed here, V01 will be 1 plus R2 by R1. See here, 1 plus RF by R, 1 plus RF by R, in this case 1 plus R2 by R1 into that voltage divider part, that is R4 by R3 plus R4. So that is our V01. In second, we consider the V2. We consider V2. Now you can see this is ground, that is also ground, and there is no input current, so voltage at this point is 0. So at non-inverting terminal potential is 0 and inverting terminal potential is V2. So the inverting terminal potential will also be 0. So due to these two ground, this potential is 0. As this is a negative feedback connection, this difference will be 0. As a result, there will be a virtual ground. So V02 will be minus R2 by R1 into V2. So the combined response, if I consider the both source at a time, the combined response that V0 will be V01 plus V02, or V01 is 1 plus R2 by R1, R4 by R3 plus R4. Now we can see that output is subtraction of the two input potentials, that is V1 minus V2 with different strength. You can see V1 is multiplied by this factor and V2 is multiplied by this factor, but still there is some subtraction. In order to achieve, so our objective for the differential amplifier, it will amplify the difference between the two signals. So if we want to achieve the difference between the multiply the difference between the two signals, that is k times, that is v0. We want to achieve v0 equals we want v0 should be k times v1 minus v2. Again, by looking at the expression, previous expression, these two gains, I'm writing the expression again, v0 equals so that was our expression. To achieve this kind of expression, that gain should be equal. That means this part and that part should be equal, so that we can take common part of it. So this gain should be equal, that is R2 by R1 should be 1 plus R2 by R1 R4 by R3 plus R4, or R1 and R1 will cancel out, so remaining part will be that. Thus, to achieve this kind of expression, we need to follow this rule, that is R1 by R2 ratio should be equal to R3 by R4. One way to achieve this by considering R1 is equal to R3 and R2 is equal to R4. So then the circuit, effective circuit will become like R1 R2 V2 V0. So it was R3, it should be equal to R1, and it was R4, it should be equal to R2 and V1. And at this condition, your output can be written as, you can take common of R2 by R1, R2 by R1, V1 minus V2. So that is the method 1, using the superposition law. In method 2, we'll use the direct loop analysis and achieve the same result. So method 2, I'll draw the circuit again. Now first we'll find this node potential VA. So that is VA. So we'll find the VA first. You can see it will act as a simple voltage divider. There will be no input current. So VA will be R4 by R3 plus R4 into V1. So that will be this node potential. Now from previous analyses, we know that this potential and that potential will be equal, because Opamp will try to minimize this difference, and as a result this node potential will also be VA. So that will be VA. If I use KCL. So then you can write at this node, at the inverting terminal, that VA minus V2 by R1, that current through R1, plus VA minus V0 by R2 equals 0, or you can write V0 is equal to 1 plus R2 by R1 VA. So that is similar to the non-inverting amplifier, and if I put the VA, it will be, sorry, so that will be the expression. And if I put the value of the VA, 1 plus R2 by R1, R3 by R3, so I'll rewrite this expression. VA, take common, 1 by R1 plus 1 by R2 minus V2 by R1 equals V0 by R2, or V0 equals VA into 1 plus R2 by R1 minus R2 by R1 V2 equals so we can achieve the same result using this method. And we can minimize this circuit once again to achieve V0 is equal to equals K into V1 minus V2.